Okay.
It's a little heavy than mine.
All right, so I can barely see. This is really. All right, so we're going to start. All right, so I'm with Jay. You guys are next. And then you guys are. Yeah, just keep going.
Okay, so our paper was the total synthesis of inostomycin A, and it was from the Journal of Angewandte Chemie by Yu, Zhang, Li, and Kang. So our target molecule is here, and it's inostomycin A. It was reported to have these R groups in a specific chiral fashion. However, upon analysis of the crystal structure, it was found that that was what was reported was incorrect, and so they corrected it to this stereocenter instead. Initially, it was isolated from the fermentation broth of Streptomyces, and this lab wanted to synthesize it for one, its complexity, and two, its pharmacological potential. Over here, we have the retrosynthesis of the molecule. Begins with aldol condensation between molecules 3 and 4. And then there's a transmetallation coupling, which is where the ligands on one metal are translated to another metal. And that's between 6 and 5 in order to form 4, as well as hydrolysis, oxidation, and a Grignard addition. And lastly, between molecules 7 and 8, there's a transmetallation coupling, again, to form an adduct. Okay, so the synthesis began with an initial known 1-amide reaction to produce 9. 9 was then transformed into 7 through a Grignard addition and a boron-mediated anti-aldol condensation, which is where the anti-molecules formed rather than the syn. From 11 to 12, there's a benzaldin protection. Here, and then there's a deprotection of the TBDSPS and a Swern oxidation as well. So from 13 to 14, a syn adduct is formed between 11 and 13 to produce 14, and then finally between 14 and 15, there is a reduction of the second carbonyl, so this one, and the protection of the terminal alcohol as seen here by the TES, and also an acyl group has been added to protect this hydroxyl. And then from 15 to 3, there's a deprotection of the hydroaromatic compound, which is this PMB, and the reason why this is attacked instead of the phenyl is because it has more hydrogens, and then an oxidation to produce the target 3.
So between 26 and 6, there's an oxidative cleavage between the two hydroxyl groups to 4, and then a Grignard addition. So you have your ethyl ketone, and then there's and then a DMP to get the ketone as opposed to the alcohol group as a secondary alcohol. Between 5 to 27, 5 is going to go through a transmetallation coupling with 6 to get 27, 27 to 28, there's a hydrolysis, and from 28 to 4, there's a tempo oxidation, and then there's a Grignard addition and a azoto double oxidation. So tempo and azoto were used coupled twice because of the fact that tempo is chemoselective and it would not do the targeting of these hydroxyl groups. It would do this one, and then Azato would do the rest of it up to get to R4. So 4 and 5 went through an anti-alcohol quantization to get 35 with a protection of the TES which is the difference between 35 and 36. 36 to 37, there's an azoto double oxidation and then a deep protection of the TES. And then there's and hydrogenation, and then chemoselective tempo oxidation to form their target of 2. And 40 is a salt formation as well that wasn't necessary to hit the target. Yeah.
Okay.
Yep.
Any questions?
Can you go back to the slide that you presented on? I'm just confused. So you say it's a reduction of the ketone, but so then where does that whole like amide group go?
So that actually is what's being reduced. So let me just double check here.
The reduction of this ketone to here will cause this to become an alcohol, and this would be a good linking group.
Yeah.
But not reduction itself.
So then is the protection the AC group going on that O, or is
No.
it the TSO?
Okay, so
the acylation here.
yeah. So initially this is formed into a primary alcohol,
Mhm.
and then we protect that with the TES protecting group,
Okay.
which like has silicon in it, and it's like a good protecting group. Anyways, and then this alcohol that's like you can see it's behind. I don't know if you can't see, but it's going behind.
Mhm.
It doesn't change stereochemistry at all, and that's why it's still behind here, and that was protected with an acyl group. Yeah, there's just like multiple, like it's G through I, there are multiple steps happening there, and so, yeah. Are there any other questions?
What's the DDQ for?
DDQ, this one, J, D protection. So DDQ is a specifically, it deprotonates hydroaromatic compounds. And yeah, that's like specifically what it reacts with.
So it's like the deep protection of this, which is like a benzyl group, and it has a higher hydrogen content than this protecting group of the 2 alcohols.
Yeah, I think there's like actually a phenyl, or maybe not phenyl, but a benzyl group with a methyl on it, and so it has more hydrogens, which makes it more,
Makes it more selective towards that group.
yeah.
Paramethoxybenzene.
What was that?
Paramethoxybenzene, right?
Yes.
How come you didn't use the hydrogenation reaction?
I
I
don't,
think it's for the selective of this group and not this.
What about the aceto
Oh.
tempo oxidation?
so the tempo oxidation is, it's used because it is more efficient, well, let me start over. So the tempo oxidation targets primary and secondary alcohols. However, the fallback of tempo oxidation is that if a secondary alcohol is sterically hindered by the molecule it's in, it will not go after those oxygens. So what happens in this reaction is that they oxidized this primary alcohol with tempo, which they could do because it was not sterically hindered, forming it into an aldehyde. Then they did a Grignard reaction where you can see the ethyl, like the 2 carbons that are added. And this was initially an alcohol in one of the intermediate steps, and then the azoto double oxidation can attack both primary and like integrated secondary alcohols, which is how you get this ring to form here, and also the oxidation of that alcohol to a ketone.
What are they oxidating?
They're oxidizing from with which one, the tempo or the azoto?
Oh, that's
The azoto is oxidizing a
This would be an alcohol group, and then it's going to do this.
yeah,
Hydroxyl type of group.
yes.
which one?
This back hydroxyl.
Which one is oxidating? How is it cycling?
azoto is a catalytic, like, radical reaction, so,
Okay. You guys want to make anything?
No,
no.
we don't.
There's a lot of radical chemistry.
Yeah, it's a very,
Alright.
yeah.
At least we're honest.
Alright, thank you.
Cool.
Escape, then go to close out, yeah, note number 3.
Oh, what you saying?
Yeah. Ready?
So hi, I'm Chase and this is Emily, and we're going to be talking about total synthesis and stereochemical reassignment of mandolite A. So this is a quick grocery synthesis of it, so I'll show that in a sec.
Skip through that.
So molecules 2 and 3 come together to form this precursor here, which, precursors 3 and 2 become glycosylated to form our target structure here. But first we have to make number 2. Number 2 is formed from 4 and 5, which undergo HWE olefination and Suzuki coupling to form 2, and they're from 2 cyclized precursors that are commercially available, as shown here. And so this is just a quick overview. There's 8 steps. The first step is sodium hydride steals this hydrogen, then that allows this dichlorobenzyl bromide to attack, forming this structure here. 9-BBN attacks this terminal alkyne right here, and then opens it up for hydroxylation by NaOH. And we see that here with the marked in red. And then this hydroxyl group right here undergoes DMP, turns into an aldehyde. That aldehyde gets olefinated by this HWE reagent, LiCl, DPA, and CH3CN. And then that olefinated product gets reduced by Dibol to form the pi bond here. And so that whole thing gets cyclized by Raychoff-Navsky-Bartlett cyclization with iodine and acetonitrile. And that forms this tetrahydrofuran ring right here. And then the group in red, this terminal alcohol, this primary alcohol right here, gets epoxized by this potassium carbonate here, and becomes epoxide, and then that opens it up for attack by the Grignard reagent right here to form our terminal alkyne right there. Then this benzyl ether gets cleaved by DDQ, and this secondary alcohol gets protected by TBSG, OTF. And we see that here. There's TBS. Here's our newly formed primary alcohol. That primary alcohol undergoes Des-Martin oxidation by DMP, turns it into an aldehyde. That aldehyde is attacked by Whitting-Stork-Zale olefination to form our vinyl ether right here. And then our terminal alkyne on the end here undergoes dihydroxylation by AD mix alpha, and that turns it into the diol. That diol product is protected by TBS. Those hydroxyl groups are protected by TBSCl, and as you can see, TBS groups right there. And then the primary alcohol gets turned into a phosphonate by this dimethyl phosphoacidic acid.
All right, so then we need 4 and 5 to create 2. So now we have to form fragment 4, which is 4 steps. The first one is speaking 6 and 7. It goes through a Prince cyclization. And how that happens is you're going to take the strong acid, and that's going to condense that aldehyde and that alkene right there. And then it's going to be immediately treated with that potassium carbonate to form that cyclic structure right there. It's then gonna undergo hydrogenolysis with PDCH2, and that is going to cleave that benzoic group off of there. And then, that's going to form a diol, and then the diol is going to undergo protection with this PMB group with the sodium hydroic acid in that. All right, so then we have this. Now we can see our PMB groups are protecting those oxygens, and then this right here is going to, we're going to take this oxygen up here, form a terminal alkyne through 3 steps. First is going to be the deprotection with TAF, and then Des-Martin oxidation is going to form an aldehyde on that oxygen, and then potassium carbonate with this Bestmann-Okyra reagent is going to react with that aldehyde and pull off oxygen for that alkyne. So then the alkyne is going to go through hydroboration, by this dicyclohexylborane, which opens it up for attack by that chemical borane, which is up here, that attaches, and then DDQ, like we saw in the last presentation, is going to deprotect those PMB groups on those oxygens, forming the alcohol scene. So now we have fragment 4 and fragment 5, which means we can make fragment 2. Fragment 2 is going to be a Suzuki coupling. So we have that vinyl halide as well as our organoborane right there. And we're just going to do a Suzuki coupling, and we can see the diene formed right there from that Suzuki coupling. And then finally, this alcohol right there is going to go through the same reaction that we just went over in the last presentation. That tempo under Rauch-Mezamuin conditions, that's going to be the HWE olefination, and that's going to form number 2. Finally, to form the final product, we need fragment 2 and fragment 3. So fragment 3 is 3 simple steps. So we take 23 and these oxygens are going to be protected by an orthoformate. It's going to form the cyclic structure that is going to methylate the oxygen. Then finally, this is going to deprotect that. That is going to reprotect that. And then it's going to go through an oxidation to form our final fragment 3. Again, that's going to go through a cane glycosylation to form that. Now all we need is to deprotect, and TASF deprotects, forms our final product.
Any questions? So let's go to the Bestmann-Okyra reagent.
Which one?
Bestmann-Okyra, which is towards the beginning.
There's a couple times. Is it this one or is it the one before?
Well, there's from 8 to the next slide. So what is the reaction here? Go back to 8.
Here, we can do the overview. So, that.
How does that happen?
To be honest, I'm not sure. I just know that it involves these 2 guys here, and it cyclizes through that to the tetrahydrofuran product.
So I think that alkyne right there is catalyzed by that acetonitrile to form with this oxygen to create this whole guy right there, and then this OH is what's sitting out over there.
anything you guys need to go over there? If you guys talk about something, everyone, right? You guys need to know what it is, otherwise, don't talk about it. Okay, the next reaction, so go back.
For,
Before, no, forward. No, before, when you put the iodine.
The iodide,
Yeah,
or the,
oh, attaching
go
them?
back, go back.
no, before,
This is
so
the
in
iodine.
the cyclization,
Go back.
there, 12.
Yes.
Where is the iodine coming from? What are you doing? How do you iodinate?
I imagine that, I don't know the mechanism. I imagine that this iodine is adding here, but that's,
But that was a tough one. There were a couple that it was just chemistry, we've never seen.
I just need to go over that, and then, so at the end, with MCPVA, just really quick, with MCPVA, how come they don't get the sulfone? How come they only get the sulfoxide?
So that's why they reprotected those oxygens all over here. It's because they want the MCPVA because this sulfoxide right here, that activated sulfoxide is required for the cane glycosylation. So the activated sulfoxide, is
They can get a sulfone, right?
a what?
Where you add 2 oxygens.
For here?
Yeah,
Sorry, what was
so
the
they
question?
only added 1 oxygen. You can get, that's the sulfoxide, you can also get a sulfone. Another oxygen added, right? That's
Yeah,
more common. How come they didn't get?
okay, so
Is that very
the,
easy to get?
the yield percent,
It's high.
is high for this one, but for a lot of like the different reactions, it's pretty low. And I know that they have a table for all of the different reaction conditions for every reaction. And so what happened is they did it under a bunch of like different temperatures and everything, and they found that because like it's this really low temperature, it's gonna be slower and it's gonna add the 1 oxygen.
Okay, thank you. All right, next. 33, number 4. Open number 4. Okay.
Alright, so on analysis is Caden. We are going to be talking about deoxynitromycin. So previously, several polyhydroxylated sugars have been shown to have interesting glycosidase inhibitory activity. And so they've focused on these and they've isolated deoxynitromycin as well as castanospermine from mulberry leaves, and they've both shown antiviral and antidiabetic activity. So pretty much for here, the 3 is kind of like a retro synthesis of what they're starting from. Dairy, deoxynitromycin. We'll go to the synthesis on the next slide. And pretty much the synthesis is focused on the propensity of vinyl epoxides to be attacked by amines and other nucleophiles, as well as the stereoselectivity at the local conditions.
Alright, so on the previous slide it showed the 3 reagent, but it was actually, so 3 was supposed to be derived initially from 6-hydroxysorbate ester, and then from that the epoxide was supposed to be opened, and a subsequent remolecular was going to give a derivative for the deoxynitromycin. This was not the case, however. So they instead tried to start with 4 up in the top there. This also gave some problems because when they attempted to dihydroxylize the silyl ether, it returned it to the starting material and didn't give any of the expected dial in the second, or number 6. So they actually decided to go with 5, which adds the PNB on the R group. This was able to dihydroxylize and move on to 6. So then from there, they protected the dial, and this was done with 2-methoxypropene, which gives, it looks funny up there, but it's basically this when you draw it. And then it was followed by a reduction to give the alcohol at the end. From there was an epoxidation, and after there was a Swarn oxidation followed by a Wittig olefination to give product 9, which was then, the PMB was then deprotected to give 10. And here's where they ran into like a long list of problems, and Alex is going to talk about that on the next slide. They basically did a bunch of things and moved on to 11 because that was going to give their next product, which is 12. So he'll give more detail about that. But then from 12, there was the vinyl group was cleaved, and a reduction followed to give this alcohol here. And they ran into some more problems here. There's a lot of problems. So I guess it wasn't a problem, but this was not the stereo substitute that they wanted at this time. So they wanted to verify and correct the relative stereochemistry. So they converted it to diacetate, which is 14, and they were happy with those results. It was exactly how they wanted it to be, so then they were able to cleave the isopropylene and deprotect to give the final product of deoxynitroamide.
So since we was talking about going from the mesylate, starting with 10. So in efforts to convert compound 10 to piperidine, they started with opening the ring with benzolamine and DMSO with the ethyl slate. And so they did get a good yield in this 76% yield, but the attempted cyclization via Mitsunobu protocol type reaction, so it didn't work. It actually gave a mixture. It did work, but it did give like a mixture, like I said. So this was a 1.2 to 1 ratio, and they weren't shooting for a mixture, so they scrapped that. And to overcome this problem, actually, they went to the mesylate form from 10. And it was interesting to me because whenever they made the mesylate from 10 to go to 11, it was the same reaction conditions, but they increased the temperature from 100 degrees to 120 degrees. And so that resulted in only the desired product. And that was also in a 76% yield, so very high yield as well. And they did also have minor traces of the phenylamino alcohol that was detected when they did sodium mesylate. So they took that information and kind of just thought about why that's happening, and they concluded that the epoxide ring may be opening before the mesylate displacement. So that's why there's still trace amounts left in there. And then from the piperidine 12, they just went back to the original synthesis that she describes.
The end. Any questions?
Yeah, so what's going on with Mitsunobu maybe?
So it was cyclization with just your typical triphenylphosphine and dead. So it just resulted in a mixture, and that
What are they
is,
exactly?
so the okay, hold on, I did look at this. They're cyclizing the
So it's like the
this is amine with this alcohol, I
Yeah.
believe is what they're cyclizing.
So they kick out the phenylphosphine oxide.
Yes. You said they kick off triphenylphosphine? Yeah. That is the byproduct of the
Still, do they retain this chemistry and then hydroxy group?
with this reaction, yes, right here.
Yeah.
They did retain the stereochemistry, but like I said, they weren't happy with this because of the mixture of 16. So I think once they increased the temperature and had the mesylate, they still had trace amounts, but the ratio was way up. It was 76%.
Can you justify the mechanism to get 16?
16.
So
Yeah, I mean, basically, what it's doing instead of cyclizing here is it's cyclizing
Yeah,
with
with
this
the other
oxygen
oxygen.
instead, which is why it gives this weird
yeah.
tries.
Yeah. So what were the previous step? The previous step? Just like in the previous group, there's an 80 mix alpha oxidation. Where's it oxidizing? Where's the oxidation?
Where? What group?
Hey. Where are the two hydrogen, the oxygens coming?
Oh, yeah. I'm not exactly sure what Adam's output looks like. I just know they're having problems with it on the 4.
The oxygen's coming from the terpene
Like, it could be
oxide.
coming from turkey chocolate, but that's big.
Toxin or telluride? Telluride.
Oh, yeah, true.
There's one more in J and K.
J and K. So basically, it cleaves this group here,
How?
and then,
What's J?
J
Mm-hmm.
is, OSO4, I believe.
What does that mean?
So SO4 and MO, doesn't it make the
Makes-
alkene to the alcohol? That's a oxygen.
Diol.
Diol.
Yeah, is it,
That's a diol.
is it, opposite or like, so, I think,
Same.
I mean, it really is, but,
Same addition point, it doesn't matter.
yeah, and so then from there, it,
Will they cleave it?
Lithium, aluminum, fiber.
it's cleaved by.
But actually, that's reducing.
So it's brighter than.
Well, it's followed by reduction.
Oh, okay, right here. For
Yeah.
sodium, okay.
You get the aldehyde, and then you mix.
Okay.
Okay, any other questions? No? All right. You guys are number 5, so number 5. So remember that everyone should be taking notes. You know, it's very kind of fast paced, or at least of the references, right? And also, what else? Yeah, there's been like a lot of repetition in just these 3 slides, right? A lot of reagents that are the same, steps that are the same. Certainly keep an eye for that. Alright, so, okay, we're gonna get started, ready?
Alright, so I'm Lo, that's Maddie, and we're doing the total synthesis of moranamide A. Our paper is essentially a modification of a previous paper by Kesmeyer. They also synthesized moranamide A, but our group with Ojima decided to do it with different steps and to increase the yield. We'll explain how they did that. Go to the next slide. So this is what our molecule looks like. Moranamide A is one of several moieties of moranamide. It essentially looks like this except for R's. You have this R1, R2 group. R1 will be a phenyl, and then R2 will be a methoxy group. Actually, anyways, yeah, methoxy will actually be up here in our final product in our reaction. But anyways, moranamide A is interesting to them because they found it in the myobacterium along the seashores of Japan on the Miura Peninsula, hence its name, and it was found to have antimicrobial properties. It inhibited NADH oxidase and it stabilized actin filaments, which I'll let you guys kind of speculate why that might the importance of modern medicine.
So this is our total retrosynthesis, which will go more in detail in the next couple slides about each step. But pretty much this is our target product, and it will, well, I'll start here. So this is alcohol 8 and phenylserine 9, which were both synthesized within this paper, but since we don't have enough time, I can't really show you guys how they're synthesized. But these two go through a variation of Steglich esterification to form molecule 5, which will then react with the dipeptide 4, which is molecule 4 right there, through an amine coupling reaction. And that will give you the Kazmaier intermediate, which was the intermediate that they synthesized in the other paper, and we continued that in our, or they continued that in their synthesis. And then it'll go through a methylation and deallyation to get to our target product. So this is our total synthesis. And our first step here is taking that alcohol 8 with the phenylserine 9, and I told you it's a variation of Steglich esterification. So in class we've been seeing a lot of DCC with DMAP, and this one is EDCl, HCl with DMAP. So it pretty much does the same thing where the carboxylic acid on phenylserine 9 is going to get deprotonated, and then it's going to attack the carbon within EDCl, HCl. And then this the DMAP will come in and attack that, and then this alcohol will come in and it will kick off the ester group, leaving it with molecule 5, which is now an esterification. And then the next step is taking molecule 5, and it will deprotect this FMOC group that's on the amine. And now that that's deprotected, it can go through an amine coupling using the same reagents that the Steglich esterification went through. So it reacts with dipeptide 4, which has a carboxylic acid on it, and that will then go from an amine to an amide, right here at that nitrogen, because that's where the dipeptide will come in and attack that.
Going from 26 to 27, you can see the only thing that's really changing is this TBSO is going to the carboxylic acid. So they do that by starting off with adding hydrogen fluoride that will deprotect this TBSO into a primary alcohol. They follow it with DMP and DCM, which, you know, Des-Martin reaction changes primary alcohols into aldehydes. So we'll oxidize that alcohol into the aldehyde, and then they add these strong oxidizing reagents, I believe it's sodium chloride and sodium phosphate, to then further oxidize that aldehyde into a carboxylic acid. Going from 27 to 3, so here this R group will be alcohol, just for your information. What's happening first is they are coupling the alcohol from the carboxylic acid with this, what will be an amine here. So it's an intramolecular amide coupling reaction. First we'll add this piperidine, however, with DCM. Piperidine looks a lot like pyridine, except the ring is not, there's no double bonds in the ring, and there is a hydrogen there. It'll act as a base to deprotect that FMOC, changing this into a primary amine first. And then you have, again, what Maddie talked about, this EDCl, HCl with HOBT, hydroxybenzotriazole. Basically, anytime you see hydroxybenzotriazole, you can safely assume there's going to be an amide coupling of some kind. So it will couple, again, that primary amine with the alcohol on the carboxylic acid to form this amide here. And then lastly, they add the TBAF to then deprotect the other OTBS here to get the alcohol that they were seeking. From there, and again, our final product here will be a methoxy group, and here's your phenol. So they get the alcohol to become a methoxy group by this diazomethane. You mentioned it in class briefly. Diazomethane essentially is a CH2 with a negative on top of it connected to a nitrogen with a plus and another nitrogen. It's a common methylating reagent, so that'll come in and it'll take the hydrogen from this oxygen first and then add back on to the oxygen, creating your methoxy group here. And then lastly, you have this really gnarly ruthenium compound. essentially, this ruthenium compound is going to catalyze the dealylation of this O allyl up here, giving us our alcohol at the end within our decided product.
So pretty much like the main reaction we saw throughout our whole paper was like coupling reactions, whether it was through cyclic esterification or the amide coupling. And the total synthesis in this paper was the longest linear sequence of 21 steps, and it only generated yield of 3.2% of the muraenamide A. And the original paper that was done by Keismeyer, which you saw the Keismeyer intermediate, which is molecule number 3, that only had 15 steps in the sequence and it generated yield of 1.9%. So the yields are not that great, but our paper improved slightly, so that's good.
Any questions?
So how does the hydrochloric acid affect mechanism in the steel esterification?
The Steglich. So the HCl is just kind of attached onto it. I can draw the molecule up there if you want, but it's pretty much the same like internal part with the N, double bond C, double bond N, and then there's like a couple different R groups attached onto it, and then it was really just like .HCl, but the main part of the Steglich esterification is just the nitrogen taking the H off of the carboxylic acid, and then the then deprotonated oxygen will come and attack that carbon, move the electrons onto that positive nitrogen now, and then with DMAP, since it's the catalyst, that generally comes in and kicks off with EDCl, HCl with that oxygen group on there, and since it's in acidic conditions, an H will get picked up for the other nitrogen so that it can double bond to that. And then,
We're gonna draw it.
do you want me to draw it?
Yeah.
Okay.
And then in the meantime, no, so then how do they get rid of one DBS selectively?
Here, so with the HF, they did it at 0 degrees Celsius and only for an hour. I imagine they did that specifically because this one's less sterically hindered, so it's easy for it to grab and deprotect that. This one, they got it to go by using a stronger deprotectant, TBAF, and they let it sit at 50 degrees for 14 hours. So I'm assuming that gave it more time to get in there and reach the more sterically hindered proteins. Okay. Yeah.
No, that's okay, just not the mechanism, just the reagent.
Oh, just the reagent? Okay. So I can explain the mechanism a little bit better. So
Yeah, no, we don't have time for it. Just, yeah,
that is the EDCl HCl.
What is EDCI?
What?
EDCI.
I see. So I online kept finding that might be why, because it kept just popping up as EDC online. So I figured it was the same thing, and I couldn't tell if it was an L or an I.
EDCI, HCl, that's it.
Okay. Yeah,
So just
but
the
this is
EDC
pretty
one.
much it, which looks a lot like DCC from all the other coupling reactions that we've done for the last exam.
So you guys know how to, the FMOG protection occurs, the mechanism?
How the protection occurs?
It's deprotection.
Deprotection occurs? Oh! I can't remember what FMOP looks like. No, I can't answer that question.
Yeah, so make sure you look at that. And they use what conditions to protect FMOG?
Basic.
So how come they use piperidine in one and diethylamine?
They use, what do they use? They use
That's piperidine, and then the first one, yeah.
Oh, this one up here, no. I don't know, I assume, I was gonna say it. I don't know, I assume this is a stronger base than piperidine is, and you would need a stronger base to deprotect.
They're both
I don't know.
definitely protection.
I mean, would they both be basic? Because the TBAF is a strong acid, which will do the TBSL. So we can't do like acidic conditions to remove the FMOC because that would also possibly remove the TBS.
Right now, but the question is, in one they use diethylamine, going from 5 to 26, yeah. And then the next one, 27, like very deep. That wants to remove the.
I could see it also being with like steric hindrance because the diene that they use down here is removing over here, which if it was removing up here, it has like a very bulky group right there as the other protection group. So I feel like the piperidine wouldn't be able to go in there and de-protect that as effectively as it does down here since the sterics are a lot less. But yeah, I don't really know any other like plausible reason why they would change it.
So we're going to be discussing the, this paper, which is, where to go?
All right, let's go.
Okay, got it. Oh, good, thanks. Which is the total synthesis of Virusane A. And I'm Susan and this is Keith. You want to advance it? Thanks. Basically what's important to know here is that this compound is derived from plant metabolites, and what's chemically interesting about it is that it is complex, it is inverted at all stereoisomers with the exception of C8, and it is difficult to synthesize, has multiple bridge bicycles, and it has a specialized ring within the pencil cyclic structure and 6 densely arranged stereocenters. Okay. So the original retrosynthetic analysis, the target over here, they wanted to be able to access this core, the mutinolide core, and so they had proposed this retrosynthetic analysis that would depend upon Diels-Alder 4-1 cycloaddition. However, that did not occur as expected. They had looked to prior literature for that possibility. Theirs was a more sterically hindered compound that they were seeking to work with. Instead, they just got Friedel-Crafts conjugates. So they were, because of that, they were unable to install functionality here at 14 carbon 14 because of this Diels-Alder limitation. And so this became a late stage target to install what they were looking for, which is essentially an acetate unit by alternate means. And so you can go on, thanks. So the synthesis involved ultimately an acylation followed by sequential addition. They had, the acylation was for a tertiary carbonate and the sequential addition for a secondary. They needed to depend upon ultimately selective lithiation. They had tried other means, by the way, and they wound up with undesired selectivity, starting materials, return to starting materials, decomposition, and steric hindrance issues as mentioned. So the selective lithiation was ultimately the way that they went, sorry, okay. And just to finish up, they received this coordination of lithium. They ultimately quenched it with bromide, and they set up for the Keck allylation, which enabled them to proceed and go on. Yeah, these were just, yeah, okay, just do this. This was just the various mechanisms. That's why I had these additional slides. The Sectioli was used. It's a very strong base, which is capable of dealing with weak acids. The ultimate solution, as I mentioned, was quenching the intermediate with bromide 2 to set up for the Keck allylation, and that is a radical chemical mechanism that is reflected here. Okay,
I'm gonna finish the rest of reactions of the skin. So at the Keck allylation, we got the molecule with this ester group and this triple bond here. This molecule will went through a reaction reduce LAH to reduce the ester to an alcohol here. After that, this molecule goes to the ozonolysis. The ozonolysis will apply to this double bond here, and this is a ozonolysis reaction. So the double bond here will become an aldehyde, and the OH group of this molecule will attack the aldehyde group, and the hemiacetal will be created, and we got the product 79, the molecule 79. So the molecule 79 will then go through went through a Dess-Martin oxidation, in which the secondary alcohols here was oxidized to a ketone here. And the molecule 13 went through a fragmentation to produce the final product. And this is the mechanism I propose. So the oxygen of aluminum oxide will attack the carbonyl group of the ester, and then to make the alkoxide leave. So this alkoxide is a nucleophile and will join the reaction later. So the molecule 13 was first formulated at this oxygen, and because of the formation, it will make the carbon number 3 become the carbon cation, and the nucleophile will take hydrogen away from carbon 2, and the electrons here will move here to make up the carbon cation to create the double bond, and we got the final product. That's it. Yeah.
Any questions?
Can you go to the slide with the overall scheme of these?
Yes.
So would you guys have labeled the Keck or oleation? Is that what they named it, or is that what they called it in the paper?
Yes.
Or referred to it as?
Yes.
Isn't that also a Steely coupling?
Yeah.
No,
It's not issue.
it's not
Oh, sorry.
From
it's
76.
it's different. I
Yeah.
think
It's a radical.
show the slide.
Yes, I can show you the mechanism. Oops.
Now, just really quick, just what's the difference between a heck? Let's go back. Yeah, we don't have. Let's go back to the scheme. No
What
mechanism.
was Steve?
Yeah, just there. So what's the difference between a cake and that? How come that's not a cake? This attributed thing would be something like Stevie, anything.
Yeah, because they both use tin.
Right. So what's the difference here?
Well, this is a radical mechanism, and
Yeah, that's it. Just stay there. No,
so
just stay on the main scheme.
yeah, it's
Yeah,
but that's the
yeah,
difference.
just annihilation, right?
Mhm.
No annihilation. So what's the first thing?
Okay, so it's an acylation, and that was the first step applied to the secondary carbamate, and the tertiary rather, and the sequential addition applied to the secondary carbamate. When they used the
So what's the carbon in diabetes?
Yes. Sorry. Yeah, so for the that would be the reflection of the tertiary. Okay.
What's CDI for?
So which is what, I'm sorry?
CDI?
Oh, the CDI, that was, stands for,
Yeah.
I'm sorry, I,
Draw to make it.
yeah, I had drawn it, that's why I was,
Okay, next group,
yeah.
next group, yes.
So it's the, carbonyl, diimidazole, CDI.
Alina, yeah, 6 minutes. I'll be waiting.
How do we, progress?
Got
How do we move to the next one? You got it, okay, so that.
I'm Anna, and this is Sabrina, and we're doing the photosynthesis of Roscoe and C. This was from the University of Sydney. It was published in 2014 in the European Journal of Organic Chemistry. So Hillsporians were first isolated from mudpasts from a sunflower cordia in order to develop new alleochemicals. And alleochemicals basically function like herbicides, so they're trying to develop new types of herbicides. And so today we're only focusing on Hillsporin A, although Hillsporin A and C are diastomers. So the first thing that happened was with our 15 to 16, phenylation happened, and N-butyllithium deprotonates the terminal alkyne and reacts it with a prenyl bromide to give the enol 16. From 16 to 17, it was a reduction of alkynes to alkenes. Lithium aluminum hydride gave the E-configured diene. From 17 to 13, this was a Mitsunobu coupling reaction with the 4-methoxy M-cresnol, which is 18. And that gave us the 13. 13 is our precursor to a Claisen rearrangement. So from 13 to 14, they reacted it with a Lewis acid catalyst, dimethyl aluminum chloride at low temperatures, and that was to protonate this oxygen atom at the alphenyl ether portion. And this was a linear synthesis, 4 steps, and the overall yield was a 62%.
Alright, so once they got this product number 14 from the Claisen rearrangement, they decided to change out the hydroxyl group for an acetate group. And they did this because acetate group is an electron withdrawing group, and they thought that the aromatic ring is electron rich, and it would hinder it from undergoing a Sharpless 80 reaction. So Sharpless 80 reaction is from 20 to 21 and 22. 80 stands for asymmetric dihydroxylation reaction. So this 80 makes alpha consists of an osmium catalyst, potassium carbonate, potassium ferrocyanide, and a chiral ligand, which enables it to give the preferred 21 product over 22. So the diastereomeric ratio is 5 to 1 in this case. And then they removed the acetate group using methanol and potassium carbonate, so we retrieved this OH group. Right, so once they got 23 with the correct stereochemistry, they oxidized the hydroxyl group using steric ammonium nitrate. So they got this ketone over here, and then they treated it with cesium carbonate in order to close this ring. And this reaction from 4 to 2 to 1 is called an oxo-Michael addition. So this is a 1,4 addition
of a nucleophilic oxygen to a conjugated system. So in this case, we have this oxygen right here, which is nucleophilic, attacking this carbon, which is the conjugated system, in order to form these two products. So what they were trying to isolate is this helisporin A, but they got it in a 1-to-1 ratio. Or I guess technically they weren't trying to isolate either one selectively, they just got both. So we got 22% of A and 20% of C.
Any questions?
They try to purify any of those, I know it's like poly.
So from 4 to 1 and 2, they use flash chromatography, and most of it is using column chromatography of some sort.
And then how they isolated the 23 and 24, they also used chromatography. So they did a lot of columns.
So which oxygen did you point out on your next slide to do the sensitization?
This one?
That's CAN, right? So serine ammonium nitrate. Okay, so go on to the previous one. The other one. There. So what is protonating? What? On 13 to 14. It means
13 to 14. So they used the Lewis acid catalyst, which was the dimethyl aluminum. So this was used to protonate this this oxygen.
or not to protonate.
So after rearranged,
So one of the things that they pointed out in this paper were they were trying to use different reagents to actually perform this Claisen rearrangement, and they found that using this Lewis acid was capable of protonating this alcohol specifically.
yeah, when they used the other reagents, it did not go through, and what happened was this double one. It would get
Yeah, it reacted and then hydroxyl group was here instead of.
It's a point your 3,3 symmetric rearrangement.
So if we're counting, it would be that 1, 2, 3. 1, 2, 3. If I'm counting correctly.
But a Lewis acid doesn't proton. A Lewis acid is about electrons, right? So probably what's going on is that the oxygen
in the paper.
binds to the Lewis acid.
In the paper it says using a stronger carboxylic acid, trifluoric acid, did not lead to rearrangement. It allowed for tri-substituted alkenes to participate in the hydration reaction upon aqueous workup. It was clear from this data the oxygen atom of the aliphenyl ether portion of 13 could not be protonated by interfacial water or Bronsted acid. Attempted, therefore rearrangement was unproductive. So when they did use the other reagents that they tried, it didn't work. And the only thing that did work was the Lewis acid catalyst. And they say, we therefore resorted to the Lewis acid catalyst treatment of the compound 13 with dimethyl aluminum chloride at low temperatures gave a smooth conversion to the desired product. And it was the only thing that worked.
Yeah, but there is no proton. You have to show me do the mechanism and show me where the proton is coming from pentane or dimethyl aluminum chloride.
I'm not sure.
It's a Lewis acid, and then you can protonate later. That's right.
Hi everybody, my name is Willis Biguet,
Christiana Murray.
and our project was the synthesis of the enantiomer hydromorphone. This paper was published by Vimel Verghese and Professor Thomas Hudlicki at the University of Rock University. It is, as of 2014, this was the shortest synthetic route for the enantiomer of hydromorphone. It is imperative that we note that the enantiomer is not biologically active, where the counterpart, hydromorphone, is biologically active and is used to treat acute and chronic pain.
So this isn't the first attempt to synthesize hydromorphone. However, the paper does begin with a general overview of key highlights of the synthesis. So you can see a coupling reaction in Unit 1 between the phenyl and another cyclic compound. They use a Mitsunobu reaction to do that. And then following that, they do an oxidation, dearomatization to form the diene. And then what they do is they actually do an intramolecular DS-Alder 6th edition, and that has never been done before. They use intermolecular DS-Alder additions to get the hydromorphone backbone skeletal structure. And then from there, they do some workup with trifluoroacetic acid to re-aromatize the phenyl ring, and then following that, they do they form the amine bridge and an oxidation step to get the enantiomer. But the paper does reference, and I found this really interesting, that you can actually manipulate the stereochemistry to get the biologically active enantiomer, and they do that by doing a double inversion of the Mitsunobu reaction to get this bond flip over. And then you can also manipulate your intermolecular DS-Alder reaction to actually get the amine bridge to come on top of the skeletal structure.
So getting into a little bit more of the details here, we're starting with compound 8, beta-bromoethylbenzene. It's going to be dihydroxylated by an enzyme found in E. coli. It'll give us compound 9, which will undergo 2 reactions. The first being a selective reduction by potassium azodicarboxylate. And it's going to reduce the alkene inside the ring, and then we're going to be putting on, or they put on a acetyl protecting group with 2,2-dimethoxypropane. Since that is protected, they performed an SN2 reaction, replacing the bromine with the amine. And from there, they removed the acetyl group with 3 molar hydrochloric acid and placed a block protecting group on the amine, which we see here in the boxed compound. From here, they added further protecting groups to this hydroxyl group with TBS. It is noted in the paper that TBS did not attack here the hydroxyl group, and it is believed due to the steric hindrance of the block group that was there. Reaction F is their experimentation between protecting groups of Bach and tosylate, and they found that Bach produced higher yields at the very end of the enantiomer of hydromorphone.
All right, so the second precursor that they prepared before they did the Mitsunobu reaction started out with an acetylation using anhydride acetic acid, anhydride, acetic anhydride. And that was followed by the non-protecting group, and then they removed the acetyl group by treating it with potassium carbonate, methanol, and then this afforded the precursor to the Mitsunobu reaction.
Now that we had both of our precursors, they were coupled using a Mitsunobu reaction seen in 19A. 13 and 14 are just the different protecting groups that we talked about earlier. We're going forth with 13 with the block protecting group. It is, as Cristiano noted, the Mitsunobu reaction occurring once gives us the enantiomer of hydromorphone, where the double inversion of the enantiomer produces the biologically active form of hydromorphone. From there, compound 19A, there's a Wittig reaction occurring, producing the vinyl alkene, and then just a removal of the non-protecting group using zinc bromide to give us compound 21.
All right, following that, compound 21 is treated with lead tetraacetate, and that affords the oxidation dearomatization to form the beta ketone that is used in the DS-Alder intramolecular reaction to form the skeletal backbone. From there, the beta ketone is treated with trifluoroacetic acid, and that re-aromatizes the phenyl ring. And in addition, it also removes the bond protecting group from the methylamine
And then from there, it was treated with tosyl chloride, and this added a tosyl group to the methylamine as well as the phenol. And then the paper does note that in lieu of TDS, if you treat that protecting group with trifluoroacetic acid, you convert it back to an alcohol, and that will afford the enantiomer they found to form.
So getting into the final stages of our synthesis here, we are going to remove the tosylate protecting groups from the amine and the otosylate up top using lithium and terbutyl alcohol and ammonia. And that's going to also create the amine bridge on the backside, completing the hydromorphone structure, or skeletal structure. And from there, it undergoes reaction I, which is the oxidation of the alcohol or hydroxyl group on the bottom, giving us our final product of the enantiomer of hydromorphone. Right?
Any questions?
Sorry, I didn't really understand the double inversion.
Right, so if you need that to look it's on the back of the slides. Right there. So this is what they refer to when they do the Mitsunova reaction to couple the two internal alcohols. And essentially what happens is you can actually perform this reaction twice and it will invert the stereochemistry, is what they were saying. So if you that's what in the paper it specifically said they did a double inversion to get the enantiomer of the biologically active hydromorphone.
Under the last slide of the presentation, you removal of the protected groups, it was done in like -78 degrees, so why is it so cold?
Probably because it's exothermic.
Because what?
Probably because it's exothermic. Usually reactions are done at a cooler temperature for exothermic.
Did I see it right that E. coli was a reagent?
Yes.
Yes.
Yes. Isn't that really cool? Yeah, actually, that's what gets the dihydroxyl group from like the beta bromo ethylbenzene. That's how you get the dihydroxyl groups. And it's also stereospecific, so that was really cool.
Is that common? People use E. coli?
Yeah, it actually is. We actually
Found 2 or 3 other papers that reference the same.
and it also has its own Wikipedia page that lets you know that it's common.
So it has some purpose.
So what's the enzyme that takes care of that?
Actually, I do have it. Can you go to the back slide?
I use the name.
I don't
Yes.
have it memorized, but it's
Okay, next group.
So I'm Kyle Brown. And I'm Dylan Richardson, and we did the synthesis of plusrachidone. So this was the first total synthesis of the plusrachidone was done by the University of Hannover in Germany. The paper was published in 2001. So this compound has potential anti-tumor properties due to its high cytotoxicity in mouse cell cultures and HeLa cell lines. The paper also mentioned that it has similar structure to other anti-tumor drugs. We're looking at the retrosynthetic path. We have the rachidone on top. They did a multi-convergent synthesis where they synthesized fragments A, B, and C. They then did a Wittig reaction where they used the phosphonium salt on fragment B with the aldehyde on fragment C. They then followed this with the Heck coupling where they coupled the terminal alkene in fragment A with the vinyl iodide in fragment B. So they first synthesized fragment B, and they did this by taking a terminal alkyne and converting it into an alkene. They did this through carbometallation, which they specifically used the Schwartz reagent, which is a zirconium organometallic compound. This is done through a hydrozirconation, which they said is a concerted mechanism where the zirconium adds anti-Markovnikov. They then quenched this with iodide, which then replaced the zirconium metal. They then followed this with a DMP oxidation, where they oxidized the primary alcohol to an aldehyde. This aldehyde can then react with the Still-Gennari reagent, which is here. And this mechanism is similar to the Horner-Wadsworth-Emmons reaction. Something to note is that the Still-Gennari reagent is regioselective for Z opens. They also used a Crown 6 ether to cage the potassium ion and potassium bis trimethylsilyamide. This would activate that base, which could then help promote allyl formation. Following this, they did a reduction with dipol H, which reduced the methyl ester to a alcohol. This alcohol can then be converted to a bromine using an Appel reaction. An Appel reaction, they use the tetrabromomethane and triphenylphosphine. This mechanism is similar to the Mitsunobu reaction. This can then be converted to a phosphonium salt, which they use tributyl phosphine, and this goes to an SN2 reaction to have our final fragment B.
So then they started synthesizing fragment C, and they began that in the top right there with an oxodeals outer. But prior to actually putting in the diene and dienophile, they mixed up a titanium-based catalyst called titanium isopropoxide with plesbinol. And basically we're thinking that created an asymmetric catalyst, which helps the selectivity of the reaction you see. And if you look at the dienophile and do some resonance structures, you see that the carbonyl oxygen is slightly negative and carbonyl carbon is slightly positive. And then on the dienophile, the alkene group on the top left corner, very far carbon is slightly negative. And so basically, when you do that, these react and you get the oxygen in the ring. Next, they reduced the ester using lithium aluminum hydride to get a primary alcohol. From there, they do an SN2 type reaction using isopropanol, and it causes an inversion of stereochemistry, which you see in 43. Next, they do a Sorn oxidation to convert the primary alcohol into an aldehyde. From there, they do a Levitic reaction, like what Dylan was saying, and that involved compound 16, which is the fragment that Dylan went over in their synthesis. And you see that the aldehyde on compound 44 reacts with phosphine salt on compound 16, that gives you 45. From there, they do the Heck coupling reaction, which involves compound 40. So this one here, you see there's a few different numbers and protecting groups at the R and the X. And so what they found, they tried it with TBS protecting groups, as well as with a carbonyl here, and they found that the D-protected actually gave the highest yields. So they used 40 here for the Heck reaction, and that, as he was saying, the vinyl iodide at 45, and then the terminal alkene of 40 reacted together, and you get 46. So 46 to 49 is a little weird. They first tried to deprotect by removing that isopropyl ester, but when they then went to the oxidation, the next steps, they got low yields. So then they went back and converted, they protected with TBS first, and then converted the isopropyl ester to an alcohol group. From there, they used selective oxidation with manganese oxide. Here, it only reacted with the allylic alcohol, which is X, and that gives you 50 here. All that was left was to deprotect. They removed their TBS groups, and they got rachido. And the overall yield of this synthesis was about 6.7%. That's everything.
Questions?
You mentioned that they got a better yield when they deprotected. Was that due to steric hindrance, or did they say?
They did not go over why that is.
Yield was double though. It was like 40-ish% with the protected and went to 80-ish% with this deprotected.
And that's even with the same alkene constituent. I think that maybe steric hindrance is.
Were they looking to protect, how many protections were they looking to?
So, I mean, here there's two protecting groups.
Two, yeah. So.
How do you think Gershon was PPTS? Is that a mechanism?
That is the one we drew out. So PPTS is like it's a benzoyl green benzoyl green with a sulfone that's negative, and then purity is the other one. And so, I actually have it written down.
Yeah, that's okay. the previous slide, headlinked reduction.
Which reduction? Like age?
Yeah, headlinked the OH. High.
Like where are we? How they go to alpha reaction?
Uphill.
So yeah, so the reduction goes from the ester to alcohol.
Yeah, what do they use?
They use diethol H. Yes.
Do you guys know the mechanism for the third reaction?
Yeah, so the triphenylphosphine will do a nucleophilic attack on the bromine, which will cause a negative charge to be on the carbon. The negatively charged carbon will then go deprotonate the oxygen. The oxygen can then, the negatively charged oxygen can then go and attack the phosphor, displacing another bromine, and the bromine will do its thing.
Triphenylphosphine oxide, right?
So what was the question?
You guys get triphenylphosphine oxide out.
Yes.
Okay. All right. Thank you. Thank you, everyone.